Do a video here on nuclear reactions. Nuclear reactions. And I'm not sure yet. We'll see how this goes, how long this takes me, if I want to break this into two videos or just one. But the first thing we want to start off doing is kind of changing how we're going to define things. Before we talked about mass in kilograms and all that kind of stuff. But now we're talking about things down in the nucleus, so we have to come up with a little better unit for that. And the unit uh, that was developed for this is the AMU, the atomic mass unit. The little symbol for it is the lowercase letter u, and it's defined as 1/12 of the mass of a carbon 12 atom. So this gives you about the mass of a single proton or single neutron. It's not exactly the mass of a single proton or single neutron, and the reason why it's not exactly the mass of one of those will make sense by the end of this whole thing, hopefully, as you'll find out why it isn't. It turns out for the mass of a proton, so for a proton, it is approximately about 1.00728 AMUs, so a little u there, and then the mass of a neutron, so same thing, mass of a neutron is about so little squiggly things, 1.008867 AMUs. And so they're very close, but they're both a little bit off of what this is, and it's defined from the carbon 12 atom, not from something else. And then, of course, one of these U's, one U, just so you can do some conversions, you need the equivalence of this, and it's about this. You can get more decimal places than this if you look in your book or something, or in other sources, but it's about 1.66 times 10 to the negative 27 kilograms. So it's a really, really small amount, which makes sense because protons and neutrons are really, really, really small. Now, a lot of times when you'll see them talk about the actual masses of different elements, they talk about two different things. They'll have the atomic mass, and you can look up some examples of this. You'll find a table that's atomic mass, and then other places you'll see nuclear mass. And the difference here is basically over here, all I did was mass the actual atom, including, so this is the nucleus mass plus the electrons. Okay? And then once you have this, over here, this nuclear mass, is basically once you subtract off the mass of the electrons. And so you take the atomic mass, it's the atomic mass minus the electron mass, and that just gives you then just the mass of the nucleus. Okay? So, or pretty much just the mass of the nucleus. There's some potential energy stuff in there that, but for the most part, it's the mass of the nucleus. Okay? And if you do this for a bunch of them, you will get some answers. You'll get a whole bunch of different masses of what the nucleus is in AMUs. And one example I can give you here is when you do this for helium-4, which is a helium with four protons and neutrons in the nucleus, and or nucleons in there, and it has a nuclear mass, so a nuclear only need one R there, a nuclear mass equal to 4.001504, or 0, not 4, sorry, I can't read my writing, that's a U at the end there, All right, 5, 0, and then let me put it as a U. It has a nuclear mass of 4.00150 AMUs, and I know what y'all are now thinking, because I'm fairly certain in the few seconds that I wrote that, you have all said, wait a second, if I take the mass of 2 protons and I take the mass of 2 neutrons, you know, these values from up here, take these two masses, and I take twice that and twice that, and I add them together, I don't get 4.0015 AMU. I get something, so just adding in 2 protons plus 2 neutrons, that actually gives you 4.0319 AMUs. And so there is a problem here, because if we just directly measure the mass of the nucleus, or indirectly measure the mass of the atom and then subtract off the electrons, you get this number. But if we add up how much 2 protons and 2 neutrons, how much their mass is total together, we get a greater number. And so this kind of looks like it's a problem, but ultimately it's not a problem, and it'll start to make sense here in a few minutes. So this energy, or this mass difference, is called the mass defect. Okay? And what you would find if you went and did this for all the elements in the periodic table, as you would go and find this, you would find that essentially the mass defect would show you that the mass of the parts, the sum of the mass of the parts, is always greater than the whole, than the mass of the whole, of the whole thing. And the reason for this is because of something called binding energy. Okay, so this mass defect, that's an important term to remember. That's, you know, the difference in the masses. But there's also a term you need to know that's called binding energy, and this is the amount of energy that it takes to basically build this. So ultimately, what this binding energy is the energy that's released when you build, when you build, or when you put together, when putting together the parts of a nucleus. Sorry, NEU. So when you put together the parts of a nucleus, there's energy that gets released. And if you think back to before, that energy would then be equal to this change in mass, because one, we have to conserve energy, and two, we have from Einstein's equation that energy equals mc squared. So as we bind these together, as we force these together to overcome that Coulomb repulsion, we are actually forcing energy to be released and forcing all of these things, the mass of some of these particles to be released as this energy, and this is the binding energy of putting together. This also tells you how much energy it's going to take to pull them apart as well, when we start talking about that kind of stuff in a little bit. This is the amount of energy that is released when you put it together, and then of course that's then how bound together they are. And this is going to be, you know, dealing with this whole mass defect of how much mass is actually missing here, and that's the amount of energy you're getting that's left over from that binding energy. Now, another thing that can be done is, instead of just doing the binding energy, turns out it's very useful if you do the binding energy, which I'm just going to write B dot E for, and we're going to do it per nucleon. Okay, this binding energy per nucleon. So if you found the binding energy for helium, you would then divide it by 4, since there are 4 nucleons in there. You'd divide it by that 4, and you'd have the binding energy per nucleon. And then if you, of course, you keep going, you do it for all the other elements. And what will happen is you'll get you can then build a graph. And you'll see a graph that looks something like this, where Down on the bottom, this is your number of nucleons. And over here, this is that binding energy per nucleon. Sorry for the handwriting. But ultimately, the shape of this graph and the kind of properties that go on this graph is pretty interesting, because what kind of happens, and there's some little like wiggles and stuff in here, and this isn't a perfect drawing, but basically what happens is you start and it just ramps up. The binding energy per nucleon ramps up real fast, and then it peaks and it starts to go back down like this. Okay? And at the top of this, at the peak of this, up here, is actually iron. Iron is there. And this makes iron a very, very stable element. So if I were to ask you, like, if you were going to start just sticking nucleons together, you had a bunch of nucleons, you're going to stick them together, how many would you stick together to get the most energy released? And that would be iron. If you start going beyond iron, then this starts to drop back down, and you don't get as much energy for every nucleon you add. So you'd add them all up to, you'd make an iron element, an iron atom, and then you'd put that to the side and then start making your second iron element, because it's going to get you the most binding energy per nucleon. If you stop before you get to iron and you start making other elements, like say you make up the helium and then you make a helium atom, then you put it aside and make another helium atom, put it aside, then you're not getting up to this maximum here, and you're not getting all the energy you could. So you want to actually make up to iron. It would be the best for you. And it turns out that as far as we can tell in stars, with what happens in the stars, they go through making and the heat and pressure in the middle of a star start putting these together and making these, and stars stop making. They basically die when they start making iron, and then ultimately they're just a big giant ball of iron that's left over when it goes old and dies and stops reacting, and that's what you have here, is just this iron. And then for any elements that are greater than this, your uraniums, your golds, all these heavier elements, heavier than the iron, the only place that we've ever been able to come up with, or anybody's ever found, that is strong enough to make these naturally in the universe is through a supernova. So you'd have a star that went along, made everything up to iron, and then it could not make anything bigger than iron because it's not as energy efficient anymore, and then it collapses on itself and goes supernova, and then the energy in that supernova can actually go ahead and fuse. I haven't used that term yet, so I shouldn't say it, but go ahead and make these bigger, heavier elements, and that's a very important curve to kind of go on now. There's a little up and down wiggles in this side, but the overall basic feature is this. So this is your most stable atom that you're going to make as far as the nucleus goes. Either way, if you're over here, you kind of want to tend back towards iron. If you're over here, you want to tend towards iron, and this is your real stable area. That brings us to the next little part in the last bit of this, and it's fission and fusion. Okay, so it's fission and fusion, and you want to be really careful about this if you're taking for the IB exam, that you spell these correctly. Apparently they really don't like you to misspell these, and they won't give you credit for it. So fission is spelled with two S's, and I know I'd be in a lot of trouble with this because my spelling is not great. And then fusion is spelled with just one S. So we're going to talk fission versus fusion. What's the difference? What are they? So fusion sounds like what it sounds like. It sounds like you're fusing things together. So fusion is when you take smaller nucleus and you combine them together, or smaller nucleons, and you stick them together into a larger one. So that would be this side of the curve here, where you'd be going up, taking these smaller elements and combining them together into larger and larger elements. So fusion is combining nucleons, whereas fission is the opposite. Fission is when you break apart the nucleons. This is breaking apart nucleons, and we talked in the last video, I believe, about a type of this, and that was That was our some of our decays that we talked about, where we had a helium atom, right, an alpha particle come out of the nucleus, and that would be an example of fission. Fusion would be like if I took two helium atoms or two hydrogen atoms and I stuck the two protons together and made a helium atom. And so uh, this is what happens in stars. This is where they start combining it. So stars do this side here, and they work up towards iron. And this is actually produces more energy than fission does, but it's not as practical for use because you may get more energy, so it's more energy, but you have to actually have these at a very high temperature. But a high temperature is needed to get this to occur, and it's not something you're going to like keep in your house with something that's at thousands of Kelvin, like the temperature of the sun, to have this happen. There's long been that search for cold fusion, but it's largely now thought to be impossible to get stuff to fuse at low temperatures. Fission, we break this apart. This is the earlier nuclear bomb. This is a lot of these things where they take uranium and stuff like that, and they use it in power plants and things like that. That's fission. For fission, you can look at something like uranium 238. This is where you have 238 protons and neutrons, and then there's the uranium 235. And what you do is you find uranium, and then you have to refine it, because it turns out that the more unstable of the two, you might think it's going to be the 238 because it's the larger one and it's bigger, it's harder to hold together, is more stable. But it turns out that 235, an odd number of nucleons, is actually more unstable. So this is the more unstable because of these odd number. Now, the reason for this has to do with spin, and we haven't really talked about that just yet, so I don't want to get into that, but it's more unstable because of the spin of these things and what kind of a particle uranium-230 is versus 238 is, 235 is versus 238. We're not ready to talk about that exact reason yet, but so you would want this uranium-235, and then you could cause it to break apart if you sent a neutron into its nucleus. So here's your uranium-235. You sent a little neutron in, it would break, and it would split this into two smaller ones, and then some other little neutrons, I don't know how many, but a few neutrons would be created, and then they could go and they could collide in with the other uranium-235 nuclei. There's a little more to it than this, and we'll get into more about that later. But for right now, that would then happen, and then these would split, and it would be a nice chain reaction that would go on. Now, how much energy do you actually get from this? This again goes back to E equals mc squared, and what we're interested in then is not just mc squared, but the change in mass times the speed of light squared. So what you would do is you'd look and see, all right, what was the mass of your products? So what's the mass of these two things, like this was our initial reaction, and then what's the mass of what got produced? Okay, so like in my little example here, and so it would essentially be the mass of the reactants, right? Mass of the reactants minus the mass of the products, of what's produced. The mass of the products, take that, just find the difference in their masses, multiply it by c squared, make sure all your units are all matching up in proper, whatever unit system you're using, AMUs, electron volts, kilograms, all this kind of things for your energies and everything. Make sure you match them all up, and you do this and you get your answer. And it's just about that simple. All right, so that's about all that we really need to cover for this part. We'll have another video just to finish up this topic pretty soon.